You look up, same craters, same shadows, same lunar face staring back at you like it has for your entire life. Every single night that you have gazed at the moon, you have seen the exact same side. The far side remains hidden. A cosmic secret kept for all of human history until 1959 when Soviet cameras finally captured it. But this is not some strange accident. This is not a cosmic coincidence that the moon happens to show us one face while hiding the other. The reason the moon always shows one face is much more strange than you imagine. It is a violent story written in physics. A story that began 4.5 billion years ago with catastrophic collision, molten rock, and forces so powerful they reshaped an entire world and locked it into an eternal dance, 4.5 billion years back. The solar system is young. Earth is not the blue planet you know. It is a hellscape of molten rock and volcanic storms, no oceans, no life, just heat and chaos. Then something the size of Mars comes screaming through space toward the infant Earth. Scientists call this object Theia, named after the Greek titan who gave birth to the moon goddess Selene. Theia was not wandering randomly. It was likely sitting in a stable orbital position called the L4 or L5 Lagrange point in the Earth-Sun system, where gravitational forces balance perfectly. For millions of years it stayed there. Then something destabilized it. Maybe another planetary body pulled it loose. Maybe orbital resonances shifted. We do not know what triggered the fall, but Theia fell. The impact velocity at contact exceeded 9.3 kilometers per second. The angle was approximately 45 degrees. Not a glancing blow, not a head-on collision, a perfectly oblique strike that maximized the catastrophic result. When Theia hit Earth, the energy release was beyond comprehension. The entire proto-Earth became partially molten. Theia's iron core plunged through the still-forming Earth and merged with our planet's core. This explains why Earth has the highest density of all planets in the solar system. We absorbed another world's metal heart. The mantle material from both bodies was thrown into space. Vaporized rock, molten debris, a massive cloud of superheated material now orbiting the young Earth. Most theories said this debris disk took months or years to cool and coalesce into the moon. New simulations published in the Astrophysical Journal, letters in 2022 using 100 million particles showed something different. The moon may have formed in hours, not months. Hours. Jacob Kegeris at NASA Ames Research Center led the team. They used smooth particle hydrodynamics at resolutions never achieved before. Previous simulations used hundreds of thousands of particles. These new models used 100 million. The extra computational power revealed behaviors that lower resolution simulations completely missed. Material from Earth and Theia launched directly into orbit and immediately formed a satellite, a moon-sized body appearing in Earth's sky within a single day after the impact. This newly formed moon sat between 14,000 and 22,500 kilometers from Earth. Today, the moon orbits at 384,400 kilometers. That early moon was 20 times closer. From Earth's surface, it would have appeared 15 to 20 times larger in the sky than we see it today, a massive disk dominating the heavens. The tidal forces at that proximity were catastrophic, 5,000 times stronger than today. If oceans had existed then, which they did not for another 100 million years, tides would have been kilometers high. Not the meter-scale tides we experience, kilometers. The Earth itself was stretched into an oval shape by the moon's gravitational pull. The moon was stretched even more dramatically by Earth. If you value documented astrophysics and planetary formation history like this, subscribe. It is the best way to support our work. Also comment from which city you are hearing this from. This script is researched and factual, using sources from NASA's Goddard Space Flight Center, including their April 2025 publication on tidal locking dynamics, the Astrophysical Journal letters from October 2022 detailing high-resolution impact simulations, and Nature Geoscience from May 2025 covering isotopic evidence of moon formation. These are not popular science summaries. These are primary research publications from organizations directly analyzing lunar samples and running billion-particle computational models. Now back to the information. The young moon was spinning, rotating rapidly on its axis. It was also molten, or partially molten, a ball of liquid rock heated by the violence of its formation. Earth's gravity pulled on this spinning, molten body unevenly. The side facing Earth felt stronger gravitational attraction than the far side. This difference is called a tidal force. The force is proportional to the diameter of the object being pulled and inversely proportional to the cube of the distance between the two bodies. Cube of the distance. This means when distance doubles, tidal force drops to 1/8. When distance triples, Tidal force drops to 1/27th at 14,000 to 22,000 kilometers, with the moon's diameter of 3,474 kilometers. The tidal forces were immense. These forces distorted the moon into an elongated shape, a slight football shape with the long axis pointing toward Earth. As the moon rotated, this bulge tried to rotate with it. But Earth's gravity constantly pulled the bulge back toward alignment with the Earth-Moon line. The bulge could not keep up with the moon's rotation. There was a lag, a delay because rock, even molten rock, takes time to flow and to form. This misalignment was everything. The bulge pointed slightly away from the direct Earth-Moon line in the direction of the moon's spin. Earth's gravity pulled on this offset bulge with a force that had a rotational component, a torque. This torque acted to slow the moon's rotation. Every rotation of the moon, Earth's gravity pulled backward on the leading edge of the tidal bulge. The moon lost rotational energy to friction, internal friction, as the rock deformed. The energy converted to heat. The moon heated from the inside out as its rotation slowed. This process has a name: tidal acceleration, or more precisely in the moon's case, tidal deceleration. The moon's rotation rate decreased while its orbital distance increased. Angular momentum is conserved in the Earth-Moon system. The moon lost rotational angular momentum and gained orbital angular momentum. Losing rotational momentum means spinning slower. Gaining orbital momentum means moving farther away. The moon drifted outward as it slowed its spin. Both processes happened together. NASA's page on tidal locking, updated April 8, 2025, states that all large moons in the solar system synchronize within hundreds of thousands of orbits. For the moon, orbital period was initially much shorter because it orbited so close. An orbit at 20,000 kilometers would take only a few days. Hundreds of thousands of orbits means hundreds of thousands of days. That is a few million years at most. Some estimates suggest the moon became tidally locked in as little as 1,000 years. One source from Astronomical Returns analyzing the tidal locking formula suggests that, given the moon's proximity and the molten state reducing internal rigidity, the synchronization could have occurred within 10,000 years. The formula for tidal locking timescale is complex. It involves initial spin rate, semi-major axis raised to the sixth power, moment of inertia, a dissipation parameter called Q, gravitational constant, mass of the central body squared. Another parameter called K sub 2 ice and radius to the fifth power. Distance dominates because it appears to the sixth power in the numerator and effectively cubed in the denominator through other terms. Smaller distance equals exponentially faster locking. The moon's small initial distance and molten interior meant tidal locking happened geologically fast. Within the first 100 million years of the moon's existence, possibly much sooner, one face was permanently aimed at Earth. What does tidal locking mean? The moon rotates exactly once per orbit. Its rotational period matches its orbital period. 27.3 days to rotate. 27.3 days to orbit Earth. From the moon's surface, Earth hangs in one spot in the sky. It does not rise or set, it just sits there, slowly rotating to show all its surface but never moving from that fixed position. If you stood on the near side of the moon, Earth would always be overhead. If you stood on the far side, you would never see Earth. Not once in a billion years. This synchronous rotation is not unique. Io orbits Jupiter tidally locked. Europa orbits Jupiter tidally locked. Ganymede, Enceladus orbits Saturn tidally locked. Titan. All large moons in the solar system are tidally locked to their planets. Why? Because tidal forces are universal. Every moon close enough to its planet experiences the same physics. The bulge, the lag, the torque, the energy dissipation, the drift outward, and the rotational slowdown. Mercury is in a 3 to 2 spin orbit resonance with the Sun, rotating 3 times for every 2 orbits. Not perfectly synchronous, but still tidally influenced. Radar observations in 1965 reveal this after decades of thinking Mercury was fully locked. Pluto and Charon are mutually tidally locked. They show the same face to each other perpetually. Charon hangs motionless in Pluto's sky. Pluto hangs motionless in Charon's sky. When 2 bodies are similar in mass and close together, both can lock to each other. The Earth-Moon system is heading that way. In approximately 50 billion years, if the Sun does not destroy us first, Earth will become tidally locked to the Moon. One hemisphere of Earth will always face the Moon. One hemisphere will never see it, but the Sun will expand into a red giant in 5 to 7 billion years, likely vaporizing both Earth and Moon long before that final locking occurs. Right now, the process continues. The Moon moves away from Earth at 3.8 centimeters per year, roughly the rate human fingernails grow. This recession is measured with laser reflectors placed on the Moon during Apollo missions. Scientists fire lasers at these reflectors and measure the return time with atomic precision. The distance increases every year. As the moon recedes, Earth's rotation continues to slow. Atomic clocks show Earth's day lengthens by approximately 2.3 milliseconds per century. Not noticeable in a human lifetime. Over geological time it accumulates. 70 million years ago, near the end of the dinosaur era, a day was 23.5 hours long. Paleontologists discovered this by examining fossilized clamshells. Clams grow in daily patterns. Count the growth lines per annual cycle, and you determine how many days were in a year. 70 million years ago, there were more days in a year because each day was shorter. Go back further. 500 million years ago, Earth rotated so fast that a day was 22 hours, and a year contained 397 days. Tidal rhythmites are alternating layers of sand and silt deposited by tides. These geological records preserve the rhythm of ancient tides, revealing how fast Earth spun and how close the moon orbited. The data matches the physics. Earth spinning faster, moon closer, tidal forces stronger. As the moon moved away, tides weakened and Earth's rotation slowed. When the moon formed at 20,000 kilometers, estimates suggest Earth's rotation period was 4 to 6 hours. A day lasted 4 to 6 hours. The moon orbited Earth in just a few days. The sky changed constantly. The moon would have appeared to move across the sky much faster than it does now. But from the moon's perspective, once tidal locking occurred, Earth stopped moving, locked in position forever. Why does the moon not show us its far side? Because 4 billion years ago, tidal forces slowed its rotation until synchronization. The energy was dissipated as heat. The moon has no more rotational kinetic energy to lose relative to its orbit. It reached the minimum energy state. The configuration with the lowest potential energy in the Earth-Moon system is tidal locking. Any deviation from perfect synchronization would require adding energy to the system. Natural processes remove energy through friction, not add it. So the moon stays locked, permanently. But there is more strangeness. The moon is not a perfect sphere. It is slightly elongated, an ellipsoid with a fossil bulge. The long axis of this bulge is displaced 30 degrees from the Earth-Moon line. This shape is frozen into the moon's structure. It formed when the moon was molten and much closer to Earth at roughly half its current distance. Around 190,000 kilometers. At that distance, the tidal forces were strong enough to deform the molten moon significantly. As the moon cooled and solidified, the shape locked in place. Now the moon orbits at 384,000 kilometers, too far for current tidal forces to reshape it. The moon is too cold, too solid to flow back into hydrostatic equilibrium. The fossil bulge remains as evidence of the moon's violent thermal history. The near side and far side of the moon are different. The near side has dark regions called Maria, which are basalt plains formed by ancient lava flows. The far side has almost no Maria. It is heavily cratered highlands. Why the asymmetry? Two theories. One possibility is asymmetrical tidal heating when the moon was much closer to Earth. The near side experienced stronger heating from tidal forces, leading to more volcanic activity. Another theory involves a second moon. Some models suggest Earth briefly had two moons after the Theia impact, a smaller moon in a slower orbit. The second moon eventually collided with the primary moon in a slow velocity impact tens of millions of years after the moon formed. The impact created the thick crust on the far side, preventing lava from reaching the surface even when volcanic activity occurred. Both theories have supporting evidence. Radiometric dating shows the highlands formed 4.4 billion years ago. The Maria are younger, between 3.1 and 3.8 billion years old. It formed during a period of intense volcanic activity. NASA missions have analyzed lunar samples extensively. Apollo missions returned 382 kilograms of moon rocks. Soviet Luna missions returned additional samples. China's Chang'e missions in the 2020s have provided samples from the far side for the first time. These samples reveal isotopic similarities between Earth and Moon that are remarkable. Oxygen isotopes show nearly identical ratios. Titanium isotopes match. Tungsten isotopes match. These similarities were a problem for the giant impact theory because models predicted the Moon should be 70 to 90% Theia material. If Theia formed elsewhere in the solar system, its isotopic signature should differ from Earth. The Moon should be chemically distinct. Instead, it is almost identical to Earth's mantle. Research published in Science in June 2014 by Daniel Herwartz from Georg August Universität found tiny differences in oxygen isotopes. The differences are small, parts per million, but they exist. This proved the giant impact occurred and gave clues about Theia's composition. Theia appears to have been similar to enstatite chondrites, a rare class of meteorite with isotopic composition very close to Earth. This would explain why the Moon and Earth are so similar. Theia happened to have a composition matching Earth, even though it formed elsewhere. Low probability, but not impossible. Alternative explanations exist. A 2022 study in Nature proposed that remnants of Theia still exist inside Earth. 2 massive blobs near Earth's core, each larger than the Moon, may be buried pieces of Theia's mantle. These structures are called large, low-velocity provinces. They sit at the boundary between Earth's mantle and core. Seismic waves travel slowly through them. Computer models by Qian Yuan at Caltech show that when Theia collided with Earth at over 6 miles per second, some of Theia's mantle sank deep into Earth rather than being ejected into space. The iron-rich material cooled and solidified and settled at the core mantle boundary. It has remained there for 4.5 billion years. If true, Theia is not lost. It is buried inside our planet. And it may have influenced Earth's evolution, affecting mantle convection, plate tectonics, and even magnetic field generation. Back to tidal locking. Why does it happen? The physics is inevitable. Any moon close to its planet will experience differential gravitational forces. The near side feels stronger pull than the far side. This creates tidal forces. Tidal forces deform the body. Deformation plus rotation equals friction. Friction dissipates energy as heat. Energy loss means rotational slowdown. Angular momentum conservation means orbital expansion. The process continues until rotational period equals orbital period. At synchronization, the tidal bulge no longer rotates relative to the central body. The bulge points directly at the planet. No more lag, no more torque, no more energy dissipation. The system reaches equilibrium. The moon is tidally locked. The Earth experiences tidal forces from the moon. Earth's oceans bulge toward the moon and away from the moon, 2 tidal bulges at opposite sides of the planet. As Earth rotates, these bulges move. But there is friction between the oceans and the seafloor. The bulges lag slightly behind the direct Earth-Moon line. The moon's gravity pulls backward on the leading bulge. This exerts a torque that slows Earth's rotation. The equal and opposite torque pushes the moon forward in its orbit, accelerating it and raising it to a higher orbit. Conservation of angular momentum. Earth loses rotational angular momentum. Moon gains orbital angular momentum. The rate of Earth's slowdown depends on the size of the tidal bulges. Bigger bulges mean more friction. More friction means faster slowdown. When the moon was closer, tidal bulges were much larger. Earth's rotation slowed rapidly in the early solar system. As the moon receded and bulges diminished, the slowdown rate decreased. Today, the effect is small but measurable. About 17 microseconds added to each day per year. Leap seconds are added to coordinated universal time to keep atomic clocks aligned with Earth's rotation. Since 1972, 27 leap seconds have been added. Earth does not rotate as fast as atomic time advances. Eventually, Earth will rotate so slowly that 1 day equals 1 month. Earth will be tidally locked to the moon. Only one hemisphere will see the moon. The other hemisphere will never see it. The day will last approximately 47 current days. The moon will orbit at approximately 550,000 kilometers, 43% farther than today. But this will take an immense amount of time. Calculations suggest it would take billions of years beyond when the sun becomes a red giant. The sun will disrupt everything long before Earth locks to the moon. Some exoplanets discovered by telescopes are already tidally locked to their stars. LHS 3844be, a super-Earth orbiting a red dwarf star, was confirmed as tidally locked in a paper published in the Astrophysical Journal in April 2024. Observations from the Spitzer Space Telescope measured the planet's surface temperature at different points in its orbit. One side was much cooler than the other. The temperature difference was so extreme that the cool side never faces the star. The planet is locked. One hemisphere in eternal day, one hemisphere in eternal night. Research by Rory Barnes from the University of Washington in 2017 suggests that many exoplanets orbiting M-dwarf stars are tidally locked. 85% of detected exoplanets orbit close to their stars where tidal forces are strong. Most of these planets likely locked within the first few hundred million years of formation. If you value detailed research like this, covering tidal dynamics and exoplanet observations, subscribe. The sources here include data from the Spitzer Space Telescope mission, peer-reviewed astrophysics publications from the Astrophysical Journal, updated through April 2024, and research from the University of Washington's Virtual Planetary Laboratory. These are institutions directly analyzing telescope data and running orbital simulations. Now back to the information. Tidally locked exoplanets challenge assumptions about habitability. Planets with one side always facing their star could have extreme temperature differences. The day side could be scorching hot, the night side frozen. but atmospheric circulation might redistribute heat. Winds blowing from day side to night side could moderate temperatures and create habitable zones in between. Europa and Enceladus, moons tidally locked to Jupiter and Saturn, maintain subsurface oceans through tidal heating. The tidal forces flex their interiors, generating heat through friction. This heat melts ice and maintains liquid water beneath frozen surfaces. Europa's ocean may be 100 kilometers deep. Enceladus shoots geysers of water vapor through cracks in its ice crust. Both moons are targets for future missions searching for life because tidal heating creates energy and liquid water, two requirements for life as we know it. Tidal forces can be destructive. The Roche limit is the minimum distance a moon can orbit its planet without being torn apart by tidal forces. Inside the Roche limit, differential gravitational forces exceed the moon's self-gravity. The moon disintegrates into a ring of debris. Saturn's rings sit inside Saturn's Roche limit. They cannot coalesce into a moon. Any object trying to form inside that boundary would be ripped apart. The Roche limit for a rigid body orbiting Earth is approximately 9,500 kilometers. For a fluid body, it is 18,470 kilometers. The moon currently orbits at 384,400 kilometers, far outside the Roche limit. If the moon's orbit were to decay and it came within the Roche limit, tidal forces would shatter it. Earth would have rings. This will not happen under current physics. The moon is moving away, not approaching. But if some external force disrupted the system, if a massive object passed through the inner solar system and gravitationally perturbed the moon's orbit, inward spiraling could occur. Within the Roche limit, the moon would fragment. The near side would feel gravity so much stronger than the far side that the difference would overcome the moon's structural strength. Rock would pull apart. The moon would become billions of smaller pieces orbiting Earth in a ring system. Life on Earth would face catastrophic changes. Tides would disappear. The night sky would show a bright arc stretching from horizon to horizon. Debris would rain down as ring particles collided and spiraled toward Earth. Io experiences extreme tidal forces. Io orbits Jupiter at 422,000 kilometers. Jupiter is 318 times more massive than Earth. Tidal forces scale with the mass of the central body, and inversely with the cube of distance. Io experiences tidal forces strong enough to raise and lower its solid surface by up to 100 meters, twice per orbit, 100 meters. The entire moon flexes vertically by the height of a skyscraper. This generates enormous internal friction. Io's interior is partially molten. Heat from tidal friction drives over 400 active volcanoes. Io is the most geologically active object in the solar system. Volcanic plumes shoot 300 kilometers high. Lava covers the surface constantly. The surface is young, constantly resurfaced by volcanic activity. All because of tidal forces from Jupiter. Earth's moon does not experience such extreme forces now, but early in its history, when the moon orbited at 20,000 kilometers, tidal forces were comparable or stronger. The moon's interior was heated to partial or complete melting. Volcanic activity covered the surface. The Maria we see today are remnants of those ancient lava flows. As the moon receded and cooled, volcanic activity decreased. By 3 billion years ago, most volcanic activity had ceased. The moon became geologically dead. No plate tectonics, no volcanism, no erosion except from impacts. The surface we see today has been largely unchanged for billions of years. Every crater is preserved. Time is written in the landscape. The moon has moonquakes, not as strong as earthquakes, but measurable. Seismometers placed by Apollo astronauts detected thousands of moonquakes over years of operation. Some are thermal quakes caused by sudden temperature changes when sunlight hits the surface after 2 weeks of cold night. Surface temperature swings from 127 degrees Celsius in sunlight to minus 173 degrees Celsius in darkness. Rock expands and contracts, fractures, generates seismic waves. Other moonquakes are deep quakes originating hundreds of kilometers below the surface. These are caused by tidal forces from Earth. Even now, at 384,000 kilometers, Earth's gravity still flexes the moon's interior slightly. The strain accumulates and releases in deep moonquakes with a monthly pattern matching the moon's orbital position relative to Earth. Why do we see 59% of the moon's surface over time instead of exactly 50%? Libration. The moon's orbit is elliptical with eccentricity of 0.0549, not perfectly circular. When the moon is at perigee, closest to Earth at 363,300 kilometers, it moves faster in its orbit. When it is at apogee, farthest at 405,500 kilometers, it moves slower. Orbital speed varies, but rotational speed stays constant, and this causes the moon to rock back and forth in apparent rotation, letting us see about 6 degrees extra around the edges at different times. This is longitudinal libration. There is also latitudinal libration because the moon's rotational axis is tilted 5.1 degrees relative to its orbital plane. We see over the moon's north and south poles alternately. Diurnal libration occurs because observers on Earth's surface are offset from the Earth-Moon centerline. As Earth rotates, this offset changes, giving slightly different viewing angles. Combined, these librations allow us to see 59% of the moon's surface over time, even though it is tidally locked. The far side was invisible to humans until October 7, 1959. The Soviet spacecraft Luna 3 flew around the moon and transmitted photographs back to Earth. The first images showed a heavily cratered terrain with few Maria. Americans saw the far side directly when Apollo 8 astronauts orbited the moon in December 1968. Frank Borman, Jim Lovell, and Bill Anders became the first humans to see the far side with their own eyes. Later Apollo missions orbited and landed, mapping the near side extensively, but the far side remained less explored until Chinese missions. Chang'e 4 landed on the far side in January 2019, the first soft landing there. Communication required a relay satellite at the Earth-Moon Lagrange Point 2 because the moon itself blocks direct signals. Chang'e 5 returned samples from the near side in 2020. Chang'e 6 returned samples from the far side in June 2024. Analysis is ongoing. Will the moon ever show us its far side naturally? No. Tidal locking is effectively permanent. Reversing it would require injecting enormous energy into the system to spin the moon faster than synchronous rotation. No natural process will do this. Impacts could theoretically perturb the moon's rotation slightly, but not enough to unlock it. The moon's shape is frozen into a configuration that reinforces tidal locking. The fossil bulge, the mass concentrations called mascons beneath the Maria, all create gravitational asymmetries that stabilize the current orientation. Even if you could spin the moon faster, tidal forces would immediately begin slowing it back toward synchronization. Within geologically short time, thousands to millions of years, depending on how much energy you added, the moon would lock again. The same face that early humans saw is the same face you see today, the same face that dinosaurs saw 65 million years ago, the same face that the first multicellular organisms in Earth's oceans saw billions of years ago when the moon was larger and closer and brighter in the sky. That face has watched Earth for 4 billion years. It will watch for billions more until the sun dies. The moon's locked gaze is not unique or special. It is physics, inevitable physics. Every large moon does it. Every close planet does it. Tidal forces are universal. Friction is universal. Energy dissipation is universal. The mathematics is elegant. Gravity pulls unevenly. Bodies deform. Deformation lags rotation. Lag creates torque. Torque slows rotation. Conservation moves the orbit outward. Process continues until rotation matches orbit. Equilibrium. Lock. Forever. And the strangeness is that this same process is happening right now. Earth and Moon continue their slow dance. Moon drifting outward at 3.8 centimeters per year. Earth slowing its rotation by 2.3 milliseconds per century. Angular momentum flowing from Earth's spin into the Moon's orbit. The system evolves toward mutual tidal locking where Earth and Moon show the same face to each other permanently. That final state will never be reached because the sun will intervene, but the physics does not care about the sun's timeline. The physics just keeps grinding. Tidal bulge, friction, torque, energy loss, orbital gain, every day, every century, every million years. The mechanism that locked the moon 4 billion years ago is still operating today. Still moving the moon away. Still slowing Earth's spin. Some have asked if Earth could become tidally locked to the sun. The timescale is too long. Earth orbits at 150 million kilometers. Tidal forces scale with the cube of distance. At that range, solar tidal forces on Earth are weak. Calculations suggest it would take longer than the age of the universe for Earth to tidally lock to the sun. Venus is closer, but has been hit by catastrophic resurfacing events that may have reset its rotation. Venus rotates retrograde, opposite the direction it orbits. This is unusual. Impacts, or tidal locking to the sun, followed by atmospheric tides reversing the rotation, could explain it. Mercury is in a 3-to-2 resonance, not 1-to-1 synchronous rotation, because of its high orbital eccentricity. Eccentric orbits can stabilize resonances other than 1-to-1. Tidal locking shapes the architecture of planetary systems. The habitable zone around red dwarf stars sits close to the star because red dwarfs are dim. Planets in the habitable zone orbit tightly. Tidal forces are strong. Most such planets lock quickly. If life exists on planets around red dwarfs, it might live on tidally locked worlds with permanent day and night hemispheres. Biology would adapt. Plants on the day side could have heat resistance. Animals might migrate along the terminator. the boundary between day and night, where temperatures are moderate, weather patterns would be extreme. Constant sunlight on one side drives strong winds toward the night side. Hurricanes perpetual and stable. Ice sheets kilometers thick on the night side. Life could exist in the twilight zones or in subsurface oceans heated by geothermal energy. The moon's tidal locking has affected Earth's evolution. Tides, driven by the moon, mix nutrients in coastal waters. Tidal pools provide unique environments where complex chemistry can occur. Some theories suggest life originated in tidal zones where wet-dry cycles concentrate organic molecules. The moon stabilizes Earth's axial tilt. Without the moon, Earth's axis would wobble chaotically over millions of years, causing wild climate swings. Mars has no large moon. Its axial tilt has varied from 0 to 60 degrees over geological time. This causes extreme climate changes, ice ages, and warm periods cycling unpredictably. Earth's climate is more stable because the moon's gravitational influence dampens axial precession. Intelligent life may require stable climate over hundreds of millions of years. The moon might be necessary for humanity's existence. In 2023, researchers published findings in Nature suggesting that remnants of Theia buried inside Earth create mantle plumes. These plumes drive volcanism in places like Hawaii and Iceland. Hotspot volcanism may be linked to the giant impact 4.5 billion years ago. The moon's formation and Earth's geology are connected in ways we are still discovering. Theia's core merged with Earth's core. Theia's mantle partly ejected to form the moon and partly sank to the core mantle boundary. The remaining pieces influence Earth's internal dynamics today. The impact that created the moon shaped Earth's structure permanently. Could Earth have formed without a moon? Yes. Venus has no large moon. Mars has 2 tiny moons, Phobos and Deimos, likely captured asteroids. They are so small that tidal forces between them and Mars are negligible. Mercury has no moon. Many planets in the solar system lack large moons. Earth is unusual in having a moon so large relative to the planet. The moon's mass is 1/81st of Earth's mass. The moon's diameter is more than 1/4 of Earth's diameter. No other planet in the solar system has such a large moon relative to its size except Pluto with Charon, and Pluto is a dwarf planet. The Earth-Moon system is almost a double planet. Some scientists classify it that way. The barycenter, the point around which both bodies orbit, is inside Earth, but only about 1,700 kilometers below the surface. For comparison, the Sun-Jupiter barycenter is outside the Sun's surface. The moon's size and proximity make it unique. The Apollo program returned 382 kilograms of lunar samples. Analysis revealed the moon has far less iron than Earth. The moon's core is tiny, about 1 to 2% of its mass. Earth's core is about 30% of Earth's mass. This difference confirms the giant impact theory. Iron sank into Earth. Lighter mantle material was ejected. The moon formed from mantle material, so it is iron poor. The moon also has very little water, parts per million in some minerals, but essentially dry compared to Earth. Hydrogen isotope ratios show some water molecules match Earth's water, suggesting contamination from solar, wind, or comets. But bulk lunar composition is bone dry. Heat from the impact vaporized volatiles, water, carbon dioxide, nitrogen, all boiled away into space. Could the giant impact have happened differently? Other theories exist. The co-formation theory suggests Earth and Moon formed together from the same disk of material. This does not explain the compositional differences or the Moon's low iron. The capture theory suggests the Moon formed elsewhere and Earth captured it gravitationally. This requires extremely precise conditions. Orbital mechanics make capture unlikely without a mechanism to dissipate energy. Fission theory suggested the Moon split off from a rapidly rotating early Earth, and this does not explain angular momentum distribution or isotopic similarities. The giant impact theory has the most supporting evidence. Isotopic analysis, orbital dynamics, computer simulations, lunar sample composition, all point to a collision between proto-Earth and a Mars-sized body 4.5 billion years ago. Recent simulations allow for variation. Some models suggest Theia was smaller, with a grazing impact. Others suggest Theia was larger, with a more direct hit. The mix of Earth material versus Theia material in the final moon depends on impact angle and velocity. A steep impact leads to more mixing. A shallow grazing impact leads to less mixing. A steep impact matches isotopic data better because thorough mixing explains why the moon resembles Earth so closely. Oxygen isotopes in Earth and Moon are identical within measurement precision. This requires efficient mixing during the impact. If the moon were mostly Theia material and Theia formed far from Earth, isotopes should differ. They do not. So either Theia had a composition matching Earth coincidentally, or the impact mixed materials thoroughly. Models favor thorough mixing. Researchers continue refining simulations. As computational power increases, models include more physics. Thermodynamics of phase changes, viscosity of partially molten rock, magnetic field interactions, atmospheric stripping. Each refinement changes the predicted outcome slightly, but the core story remains collision, debris disk, rapid formation, tidal locking within tens of millions of years, the moon showing one face to Earth ever since. In 1959, when Luna 3 photographed the far side, expectations were that it would look similar to the near side. It did not. The far side is dramatically different. Almost no Maria, heavily cratered highlands. Why? One explanation is the thicker crust on the far side. Basaltic lava flows forming Maria require thin crust. On the near side, the crust is 30 to 40 kilometers thick. On the far side, it is 50 to 60 kilometers thick. Lava breaking through 40 kilometers of crust is possible. Breaking through 60 kilometers is much harder. Even during peak volcanic activity 3 to 4 billion years ago, lava rarely reached the surface on the far side. So the far side remains highlands, ancient cratered terrain, preserved from the heavy bombardment period 4 billion years ago. The heavy bombardment was a period roughly 4.1 to 3.8 billion years ago, when the inner solar system experienced intense impacts. Asteroids and comets left over from planetary formation rained down on terrestrial planets and moons. The moon was pummeled. Craters layered upon craters, large basins formed from massive impacts. These basins later filled with lava to form the Maria. The bombardment ended around 3.8 billion years ago. Since then, impacts have been less frequent. The moon's surface is a time capsule. No erosion, no plate tectonics. Every crater preserved. The oldest terrains are 4.4 billion years old. The youngest Maria are 3.1 billion years old. Between those dates lies the entire geological history of the moon. Earth's surface is constantly recycled. Plate tectonics subduct oceanic crust. Volcanism creates new crust. Erosion wears down mountains. The oldest rocks on Earth are 4 billion years old. From small, isolated locations in Canada and Australia, most of Earth's surface is less than 200 million years old. Ocean crust averages 60 million years old. Continents preserve older rocks, but erosion and metamorphism alter them. The moon preserves pristine ancient surfaces. This makes the moon invaluable for understanding early solar system history. The impacts recorded on the moon also occurred on Earth, but Earth's geology has erased them. The moon remembers. Tidal locking is why we rely on the moon to study early solar system history. Because one side always faces us, the near side was explored extensively during the space race. Apollo astronauts walked on the near side. Soviet robotic missions sampled the near side. Only recently have missions reached the far side. Communication challenges complicate far side exploration because Earth is not visible. Relay satellites are required. China's Kuiqiao satellite orbits the Earth-Moon L2 Lagrange point, providing communication relay for Chang'e 4 lander and rover. Future missions will require additional relay infrastructure to explore the far side thoroughly. The fossil bulge on the moon is evidence of a violent past. The moon solidified when it was closer to Earth. Tidal forces strong enough to deform molten rock shaped the moon permanently. Now the shape is frozen. The moon cannot adjust. It is too cold, too solid. The bulge remains as proof of forces that no longer act at their original strength. The moon is a relic of its own history. Every aspect of its structure tells a story. The locked face, the Maria, the highlands, the basins, the crust thickness variations, all result from formation conditions and subsequent evolution. If the moon were not tidally locked, what would we see? Both sides visible over the course of a month. The moon would rotate independently of its orbit. From Earth, we would see the entire lunar surface over time. The far side would become familiar. Maria patterns would shift in and out of view. The face would change nightly. But this is not the case. The moon is locked. 4 billion years of tidal torque have ensured one face aims at Earth perpetually. The physics is complete. The equilibrium is stable. Nothing short of a catastrophic impact will change it. And even then, tidal forces would relock the moon within geologically brief time. The moon's distance is measured with millimeter precision, using laser ranging. Reflectors placed by Apollo 11's 14-inch Kardashev and 15 missions, plus 2 Soviet reflectors from Luna missions, allow precise timing of laser pulses. Light travel time from Earth to Moon and back is about 2.5 seconds. By measuring this time to picosecond precision, distance is calculated to millimeter accuracy. Data collected over decades confirms the moon recedes at 3.82 centimeters per year on average. Variations occur because Earth's rotation rate fluctuates slightly due to changes in ice mass distribution, ocean currents, and atmospheric circulation, but the long-term trend is clear. Moon moving away, Earth slowing down, tidal locking progressing toward mutual synchronization. The final state, mutual tidal locking, will never occur naturally because the sun's death will intervene first. In 5 billion years, the sun will exhaust hydrogen in its core. It will expand into a red giant. The sun's outer layers will reach Earth's orbit or beyond. If Earth is engulfed, it will be vaporized. If Earth survives outside the sun's envelope, atmospheric drag from the sun's extended atmosphere will cause orbital decay. Earth will spiral into the sun. Either way, the Earth-Moon system will be destroyed long before mutual tidal locking completes. The physics says it would take 50 billion years. The sun will not allow 50 billion years, but the process continues regardless. Tidal forces do not care about the sun's timeline. They operate according to gravitational mechanics. Moon pulls on Earth. Earth pulls on Moon. Tidal bulges lag. Torque acts. Angular momentum transfers. The dance goes on. Every moment of every day, the Moon drifts a microscopic distance farther away. Every century, Earth's day lengthens by 2.3 milliseconds. The accumulation over geological time is profound. A mechanism older than complex life on Earth. Older than photosynthesis. Older than continents. The same physics that locked the Moon's face 4 billion years ago is still shaping the Earth-Moon system today. The reason the Moon always shows one face is not a coincidence, not a quirk, not a special arrangement. It is the inevitable outcome of gravity acting over billions of years on a satellite orbiting a planet. Differential gravitational forces create tidal bulges. Rotation creates lag. Lag creates torque. Torque dissipates rotational energy as heat. Energy loss slows rotation. Angular momentum conservation raises the orbit. Process continues until rotation synchronizes with orbit. Equilibrium. Lock. One face aimed at Earth. Forever. All large moons do it. All close planets do it. Physics demands it. The Moon had no choice. Tidal forces ground its rotation to a halt 4 billion years ago and locked it into synchronous rotation. The far side became hidden. The near side became the only side visible from Earth. And so it has been for the entirety of Earth's geological history. Every eye that has looked up at the Moon has seen the same craters, the same Maria, the same face. The Moon's gaze is eternal, locked not by choice, but by the unyielding mathematics of gravity and time.